In this video, we're going to be looking at problem set 8, question 1, part D, and we're asked to state and assess the assumptions that are required to be met in order to use this model. So these are the assumptions for any regression model that we need to make sure are in place, that they hold true. So the first one is that we have a randomly and independently selected sample. In the problem itself, it said this was a random sample, so we're going to assume this is true. There's no reason to believe that it's not true. There's no formal test for this. We need to know the background of the study. So for now, we'll just assume this is true. We need to have normally distributed data. Now remember, we've got 6 independent variables, 1 dependent variable, and a sample size of 199. So if you recall the central limit theorem tells us that as long as we have samples of size 30 or more, then our sampling distribution will be normally distributed. So since our sample is much greater than 30, we can be fairly confident that the central limit theorem is going to hold true for each of these variables. This brings the next set of assumptions, and that's called the residual analysis, and there's 3 components to that. The first one has to do with that the residuals are normally distributed. So remember, the residual, we have a list of residuals. We have 199 residuals. Each residual we can figure out by taking the difference between a particular observation, for the dependent variable, so y subscript I, and we take the difference between the actual and the predicted value. And that makes another list of data that we call the residuals, and we have 199 of them. So again, the central limit theorem holds for the assumption of normality for the residuals. Now we could do formal tests for not only the variables but also the residuals, so we could do normality tests, or we could just be more informal and look at histograms or probability plots. But because we have such a large data set, we can just assume that they are all going to be normally distributed. This next one has to do with the independence of your residuals, and there is a formal test for this that I'm not covering in this video. And it's usually only concerned if you've got time in your data, involved in your data. This is a static observation at the end of the 2007-08 season for the NHL league. So we're probably not going to have a concern with independence. And again, we could do a formal test called the Durbin-Watson test, but we're not doing that in this video. This last assumption to do with the residuals is called homoscedasticity. We want the residuals to behave randomly throughout the entire data set. And if homoscedasticity holds, this will be true. We won't see any patterns between any of the variables with the residuals. So we need to plot each variable with our residuals to check for patterns. So I've provided the plots for each of the variables so we can assess whether there's any patterns. So we look at the first one here. That's the predicted value of y, so that's our y hat values. And I've plotted them against the residuals, and I've standardized them. So we have got them standardized, so they will generally run from +3 to -3. So it's easier to scale on a scatter plot. And here we definitely see a pattern. We see what's called a funnel pattern. So in this particular funnel pattern, when the predicted values of y are small, the residuals tend to be smaller in value than when the predicted values are large. So we definitely see a pattern. So that means that homoscedasticity is violated. When it's violated, we say it is heteroscedastic. So for our predicted value of y, we definitely have a problem. So for y hat, we have a problem with homoscedasticity. So this violates the homoscedasticity assumption. This often happens with the predicted value of y, and that's because we might not have enough variables in the model. So we might want to build a model with more variables and remove the insignificant variables. So it's not something that is usually a big problem, because we can just build a different model to eliminate possible problems. Now this is the predicted value, sorry, the salary, the value, the independent variable for salary and predicted and against the standardized residual values. And here we don't really see any pattern. I do give you the r-squared value. So as with the previous one, the r-squared was a very small value, very close to 0. Now with the salary, we are looking at the r-squared. It is 0. And here, maybe you might consider it somewhat of a funnel, but it's not a very serious funnel, so I would say that there is not really a problem with a pattern. So for salary, we've got homoscedastic behavior, so it's okay. For the number of games played, and remember with games played there was only a finite number, so we do have the r-squared showing up twice here, and the r-squared is 0, so there's no linear pattern. And again, we do see maybe somewhat of a pattern. It does get a little bit bigger, but it's not a very strong funnel, so I'll just say that for now there is no obvious pattern with the games played, so we have homoscedastic data for the games played variable. The weight of the player, again, no obvious pattern, r-squared of 0, so we do have no pattern. It is homoscedastic for the weight. With age, again, we're looking for any kind of funnel, linear pattern, so r-squared of 0 is telling there's no linear pattern. We're also looking for outliers, and here in the other plots we didn't see any obvious outliers. Here we might consider that an outlier, but I doubt it would be a significant one if we did the formal test for outliers. So we'll say there is no pattern, and again this is homoscedastic for this variable. In the penalty minutes, we see that there is definitely an outlier. So remember, in the original scatter plots, when we examined the scatter plot for the penalty minutes with the points earned, so back in the first video when we were looking at these scatter plots, that was an outlier, and that outlier has now shown up here. So there's definitely one outlier that if we were actually building this model and trying to fine-tune it, we would investigate this particular player. Perhaps there was some reason that we could remove it from this sample just because it is an extreme behavior that is not likely to be representative of all the players in the league, since it does stand out by itself. So there's no pattern in the rest of it, so we would have to investigate this one outlier, and then perhaps, well, we know the data would then have a homoscedastic relationship with the residuals. So for now, we will just say there's an outlier to investigate. So if we go back to this assumption with the penalty minutes, we do have an outlier. So we would say then it is heteroscedastic, pending the investigation of that one outlier and possible removal. Finally, we look at, so both the predicted value of y and the penalty minutes, they are both heteroscedastic. So both of these are heteroscedastic. And now finally looking at the team points, we don't have any obvious patterns, so there is no pattern, so it is also homoscedastic. So our assumptions have for the most part been met, except for the predicted value of y, and again that often happens. We might need to look for more variables, or perhaps when we fine-tune this model, so if we were fine-tuning the model, we would look to remove the insignificant variable of the team points and perhaps remove that outlier from the penalty minutes, and that would improve our model greatly. And we could then see if we have a better r-squared, if we have homoscedastic behavior in the predicted value of y, and build a fairly good model to predict points earned by a player based on these 5 variables, because we did find out that the team points wasn't a significant variable. Thanks very much.